So let me start. Let me begin with address of the tool. The tool may be accessed publicly by the address berlintool.eu. Okay. As soon as someone enters this address, the tool loads, and you can see the first screen. Okay. The tool consists of a series of tabs. Here we can see the first tab. In each tab there is a description, a short description that says what the user needs to do here, familiarizes the user with this tab. So if I go through it, we will see the different tabs. We will see them in detail, but there is a description always, the inputs, etc. There is also a detailed description of the functionalities and the inputs if someone hits the help button here. As soon as you hit the help button, a manual shows up with a short introduction, and afterwards the steps that the user needs to go through to reach the result. So there is step 1, the PV system data, a detailed description of what someone should enter, what are the options. I only turn the pages because this is this is what I will describe live now. So anytime you need some help, you may see the manual. So beginning, we have to enter the photovoltaic details, the details about the photovoltaic system of our building. There are two cases the user can select. The one is use my measurement, and the other is PV system location. The first one is a case where someone has measurements from a photovoltaic in the same region of the building. So I have a building, I am interested in installing a photovoltaic, and I know what is the production of a photovoltaic in my region. So I know what to expect if I install a photovoltaic on my rooftop. So I download the measurement file template. Okay, this is an Excel file where I enter the generation the power generation of the photovoltaic for every quarter of the day, for a typical day for every month. So let me download the Excel, or I may show it in the help tool. It's better. So this is the format of the Excel.
Can you please share it also with us? I mean, at the website, that maybe I would try to upload it with you together.
Yes, share what this is the format I want to show you, the format of the Excel, but also I can download it.
Yeah, if you don't, I mean, you can share the Excel file, or it's too big in the chat.
In the chat. No, it's not too big, but I think it's
okay.
It's easy to download it from the site. It's better to go to your PC immediately.
If you but
it's a link
where
here.
is the link? It's in the same website.
It's here. It says use my measurements and then download measurement file template. So clicking this, you can download. Okay.
So okay, I see. Sorry, I missed that. Thank you.
You're welcome. So you will have an Excel in this format. So each quarter and each month of the year, and you need to insert a typical generation power profile for every month. As soon as you insert the data you have, the available data, then you browse, you take the file, and then you upload it. what you have to declare is the size of the measured PV system. So this was let's assume that this was the measurements of a neighbor photovoltaic. This was a photovoltaic of 10 kilowatt peak. So you have to enter this for the tool to normalize the curve. The other option that is, I believe, more convenient is the PV system location. This option connects with a PVGIS platform, a platform that has historical data and weather data and can predict, has historical typical profiles of photovoltaic. Here you can enter, for example, me in Thessaloniki, I can enter the center of Thessaloniki, let's say. You can enter the spot and then enter the slope of the photovoltaic. And this is it. The tool downloads and has and calculates the PV generation curves on its own. You don't need to upload anything. Then the next sub step in this tab is the analysis type. So the tool has two options for PV size analysis. The one is if we want to search among several PV sizes, which is the best and the best that suits us. Or we know from the beginning what is the size that we want. So let's say we do not need a parametric size analysis, and we know that the size that we will solve is 15 kilowatt peaks, for example. Okay, these are the two options.
Angelos, what is the idea behind the location? Like, why do we need it?
The location here.
Yeah.
The location, the tool calculates the best size for photovoltaic and battery and demand side management.
Using
So
what?
In order to achieve this, it has to calculate what is the generation and what is the consumption of the building at its time instant within the year, for example. So it needs to know what is the generation of the photovoltaic. The generation.
Yeah, but the location, what does it give you?
The location of photovoltaic, a certain size of photovoltaic panels produce different power according to the different power in different regions. I mean, different in Thessaloniki, different in Iceland, different in.
Okay.
Yeah.
I understand you now. Okay.
The radiation information.
Yeah, the radiation.
All this
The radiation,
the information
the
coming from selecting the region.
Yeah, I was
the
thinking about
location.
the color of the radiation that you see, like
It's the
deep
same
red,
thing.
yellow.
It's the same thing that appears in the Excel file. It's the same information just coming from the map immediately. Am I right? It's the same information that appears in the Excel file, but you got it for your own location if you didn't measure it by yourself.
Yes, this is exactly what happens. Okay, the radiation and the temperature differs. So in each region. So let's say that I want now a parametric PV size analysis from 1 to 10 kilowatt peaks. So I have to give a range for the analysis. Then next I have to provide the PV system degradation factor. So the PV panels, the photovoltaic panels lose their ability to produce the nominal power. So you have to declare what is the degradation factor of the panels each year. And then I have to provide the hybrid inverter efficiency. So we assume here that the photovoltaic and the battery system will be connected through a hybrid inverter. Okay, and here, according to most inverters, commercial inverters, I will give an inverter efficiency of 97%. So I have completed the first tab. I go to the second one. It's the storage system. Here I have to give some technical parameters about the battery storage system. So what will be the maximum battery size that I want to examine? For
Sorry,
example.
can you go back for a
Yes?
second?
Yes,
Can
of
you
course.
go back for a second to the last one and go down? Go a little bit more down. Yeah. Now, in the PV system, you put 0.2. You mean 0.2 percentage or 20 percentage?
Is percentage. 0.2%.
0.2 percentage.
Yeah,
Okay.
in Israel, you put 2% for the first year and then 0.4 for the rest of the years, but
Okay.
Yes.
No, I just want to see that the information is in percentage is correct. I mean,
Yes.
and it's not like should be something
It's
else.
percentage. This is a good question because I forgot to say that the units, the measurement units, are here. You can see them before you enter the value. So you see PV system derating factor percentage. So you enter the percent, you lose the measurement unit, but you know it from the beginning. Okay. So this is 90.
Thank you very much.
So storage system. I need to examine my battery sizes from 0 to 5 kilowatt hours, for example. Okay, this is what I choose. I may choose a different analysis. This is what I choose now. The usable battery capacity is the usable battery capacity is declared usually at the data sheets of the commercial batteries, the batteries you may find and purchase for photovoltaic systems. And it's from 100% to 90%, 80% if it's if we talk about lithium-ion batteries. So I will give here a 90%. This means that the battery may operate from 10% state of charge up to 100% state of charge. So you have a lowest state of charge of 10%. So you lose the 10% of the nominal capacity. You have 90% usable capacity. Maximum charging rate and maximum discharging rate. This is declared here as a rate of the battery capacity. I will insert, 70%, which means that if we consider a battery of 5 kilowatt hours, this will mean that the rated power of the battery will be 3.5 kilowatts. The battery DC to DC round trip efficiency, it's also a parameter declared in the datasets, technical datasets of batteries. And I will enter a typical percentage, which is 95%. And here comes the maximum life cycles. This is also a parameter that someone may find in the datasets. It's what the manufacturer expects the battery to live. What will be the lifetime of the battery if you operate it with a let's say a usable capacity of 90%, etc., etc. I will put 8,000 life cycles here that I took it from a data set of certain provider, battery provider. So I go through the third tab now, the consumption tab. Here Okay, here we have to give several information about the consumption of our building. What is the options for the user? The user may enter the monthly energy, a typical monthly energy of the building. You can see it here. January, February, March, April in kilowatt hours. Okay. And also provide a typical consumption profile. Which country do we need to examine? I mean, I assume I want to examine my installation that is located in Greece. So I select Greece. This is necessary because we may put here some values of kilowatt hours typical for our installation, but the tool needs to know in the background what is the profile of the consumption. So we have used some typical profiles of our project partners in this, in several.
We are
Say
also
profile, you mean daily profile, like you put here like monthly information, and then the profiles is if you
Is
pick up
loaded in the
receipts, mean
background.
how, excuse me,
They are loaded in the background.
that means, I mean, if it's coming in daytime or nighttime, it's make it hourly. That's what you mean. But by profile, I
Yes,
mean,
yes,
like to
it
take the
makes,
amount, split it through the
yes,
hours. So if you pick up Greece, so it's typical to Greece. If you pick up, you have
exactly,
your Israel, then it will be split according to Israel.
there's no
exactly.
Israel in the list.
There is no Israel, I guess. Yeah, maybe we have to build one. Okay, Avi,
Yes.
we have to do that. I mean, Vladi, if you give him the information. Okay.
The other option is to use the annual energy, and again the typical country consumption and only the annual information. And of course the other is the daily power profiles, and it's the same rationale as the PV generation. You download an Excel file and you upload, you complete it with the power profile for each day of each typical day of each month, for each quarter. Okay, and you upload it in case you have a measuring device in your building, and you know what is the consumption, and you know what is the consumption per quarter of the day. So if you have this information, you may upload it. Otherwise, you select, for example, the most convenient solution for me, which is the annual energy. And I know that my building consumes 10,000 kilowatt hours per year. So I enter it and I go on. Here is an option of the demand side management. So someone may declare the flexibility of the building consumption for each month, for each season of the year, for the two time periods of the day that the photovoltaic is inactive. Okay. But in the first scenario that I will run, I will deactivate it. And so that we can compare afterwards. Here is the next tab, the charges, the electricity charges. I mean, the cost for electrical energy. There are two options, the flat pricing and the zonal pricing. We will see later the zonal pricing. I will first use some typical values of energy in Greece before the energy crisis. The charges, the breakdown of the charges are the production cost, meaning the cost for producing the energy, the network charges, usually these are charges that are the consumers may have to pay for the distribution of energy, and the other taxes on electric, on applying on electrical energy. Okay, maybe noble energy sources taxes or other. I enter here the values for Greece and the VAT in Greece. It's 6%. So I go on to the policy. I believe this is not something difficult to charge. Policy. Here, there are many policies for incentivizing renewable energy sources in abandoned. For example, here we have not considered in this tool, in our tool, the net metering option. We have considered two other options that already exist in some countries and are also proposed by the European Union in the energy to achieve the energy targets. This is the self-consumption and the pure self-consumption option. I begin with the self-consumption option. This is an option that incentivizes the user, the consumer of the building, to install a photovoltaic and a battery in order to maximize his or her self-consumption. So minimize the energy absorption from the grid. This is the incentive is that I will minimize my my dependence on the grid, so I will minimize my cost. This is so I have to maximize my self-consumption. Here, the added cost for owning a PV system that exists in some countries, in Greece, it's €0 per year. The added income that some government or local or regional government may have given to incentivize the solution of PV battery or demand side management. In Greece, at this moment, it's €0 per year, but we have them as options because in some cases they exist, or we may, if we are policymakers, we may want to examine such a scenario. And then at the last here value, I have to enter the compensation for PV energy injected to the grid. So what is the euros per kilowatt hour for the energy of my photovoltaic that is exported to the grid? Let's say it's 0.08 euros per kilowatt hour. This is the self-consumption option. When we consider the pure self-consumption, it's the exact same case, but then we consider zero compensation. So you see it's gray, we cannot take it. Zero compensation. So if we put a photovoltaic, we know that whatever power energy of generated energy from our photovoltaic is not used into the building, it goes to the grid, but we do not get any compensation. So we'll have to select the correct size. So the policy plays an important role on the selection of the correct size. So I move on to the financial. Here are system costs. What is the investment cost for photovoltaic and hybrid inverter? Let's say 1,200 euros. What is the investment cost for batteries? No, let me put this because I have some comparisons to make later. What is the investment cost for battery? Let's say 700 euros per kilowatt hour. Here I have to declare the battery annual cost decrease. I mean, why we have this option? So the tool takes into consideration that the battery you have selected to purchase, the lifetime of the battery may be shorter than the lifetime of the investment and the analysis. So you may need to purchase a new battery and replace the older one. So the tool needs to know what will be the price of the battery at the, let's say, the 10th year that you need to replace it. So I will put an 8% annual cost decrease, okay, for the battery system, based on the literature. Then we have to enter the operation and maintenance costs of the investment as a percentage of the investment cost, the subsidy for investment, if any. I will enter 0. Then the discount rate, the inflation rate, and then the electricity cost inflation rate. So the discount rate, it's 4%. The inflation rate is 2, and electricity cost inflation rate is 2. Last tab, we enter the type of analysis we need. So as I said in the beginning, there are several options for the user. The user, let's begin from the first one, can examine 9 PV and battery size combinations. This is a fast option. The tool returns a solution really fast, in some seconds, 10-15 seconds, just to and gives a picture of how what may be the needs for our building. We will see some examples. The next is an exhaustive examination. So this examines a lot of PV and battery size combinations, but the duration is a little bit longer. Then we have 2 options for optimal PV and battery size combination. The one is optimal for the maximum net present value and optimal for maximum self-sufficiency. Okay, because the user may need to see what is the most what is the investment that gives me back the most money, or what is the investment that makes my building self-sufficiency at the most, self-sufficient at the most, so independent from the grid. So we have divided these into options, and also we have provided a third option here, that it's the option for the cost-effective PV and battery size combination. These cost-effective combinations are a trade-off between the net present value and the self-sufficiency. We will see an example for each one of the analysis. Lastly, we have to enter the analysis, the years for the analysis period in years, sorry, which is 15 to 20 years, let's say, as the life of my systems. We'll put 20 years here. I will choose the optimal sizing for net present value, for maximum net present value. And then I will go to the results tab and I will hit show results. Sorry. And if I have forgotten something, I will take this message, which says, so your some of your inputs are invalid. Please check the corresponding fields. Okay, so I have to go and see and check if I have selected everything correctly, and if I have entered all the values correctly.
Agile, can I ask you something?
Yes.
If you omit here any value, does it take automatically any average value? For example, you said about the degradation, the decreased cost of the battery. If you fill it empty, does it take any?
No.
No.
You mean a default?
So you should fill all the fields. It is
You should
mandatory.
fill all the fields. Yes.
Okay.
It's mandatory. Yes. Let me see what I have forgotten here. This is because I checked every option.
Did you turn off the demand side manager?
I have, yes, just for this scenario.
Okay.
So when this happens, because I have selected and clicked everything here, just for demonstration reasons, I will make a restart to a refresh to erase the cookies.
How do you do that? That refreshing F5?
F5. Okay. Okay. And I will enter my options. Also, there is a range. This is what I forgot. Say there is a range of for the values that the user enters. Okay, if I put something that it's, let's say, a negative cost, it says the field gets values between 0 and 10,000. So the tool will provide a notation and say a comment and give some information to the user to enter a correct value. Okay. Or this field cannot be empty. You have to enter some value. Okay. Let's hope yes. Now it works. So this tool actually, in case we are examining a certain building, that we know the consumption and generation, the location of the building, and then we can try several policies, several system costs, several charges or inflation rates or interest rate, etc. And we can compare and make a sensitivity analysis and find the best case for our investment. These are the options are all the options that I have entered can be used in my further analysis. For example, now I see some results. If I click clear results, okay, then I may go back, change just a value. Let's say, okay, this is cheaper. And then go back and click here. It will be show results again, the button without the results, and get my new values. Okay. So let us see here what are the results presented in this tab. So I can see the economical and technical results and the inputs. let's begin with this. The inputs of PV and building consumption are actually the power curves that we were talking about in the beginning, the power curves of generation of power, of generation of the photovoltaic and of the consumption. So you see the time, the month, and values. Okay, I go down to the next table, that is the building consumption, typical working and not working day per month, January working, January not working, the time here, and the power. Okay, this is just to provide these tables just to be sure that you have uploaded the correct data, and of course, if you may need this data to make some further analysis at your PC, at your computer, etc., you can export them as in Excel file. Okay, and use them. In the economical and technical results now. So at the beginning, the tool gives us the load shifting schedule, which is 0 watt-hours per month per season per time zone. Of course, because we have deactivated the demand-side management capability. The next is the general data for the optimal solution. So we see that the net present value of the investment is 4,600 euros. With an internal rate of return of 12.8%, a simple payback period of 7.5 years, and the optimal size is 3 kilowatt peaks and 1 kilowatt hours of battery. Okay, this gives an investment cost of 4,600 euros and an annual self-sufficiency rate of 38%. Below we can see the monthly self-consumption rate. So the energy of my photovoltaic that is locally consumed. This is the self-consumption. Locally consumed either at the same moment of production or stored in the battery and later used. We can see that we achieve a high self-consumption, for example, in the winter months, a lower self-consumption in the summer months. Also, we can see the monthly self-sufficiency rate. Okay, this is the trend of the self-sufficiency per month within a year. Self-sufficiency shows how independent we are from the grid, the utility grid. And lastly, we can see the cash inflows and outflows for every year of the analysis period. We have selected, if you remember, 20 years for my analysis. So this is the inflows and the revenues and the costs for each year that gives us actually the net present value of the investment. Okay, these are the results for these are the results for the case that I have selected. Let's see now how I can examine something else. So now I want to examine what will be the case, the PV system size, the battery size, the net present value, the IRR, if my building has flexibility. So if I install a system and I activate load shifting, how I will examine this? I will hit clear results. Okay, so the results are lost. I will go back to the consumption tab, activate the demand side management button, enter 10% of flexibility during winter and 10% at this time zone. What this means? At the time zone from the midnight until 8 in the morning, I say here to the tool that my consumption has a 10% flexibility. Okay, so I have a consumption in these hours. The 10% of this consumption of these kilowatt hours may be shifted. This is divided for every season. and for these two different time zones. So I select the same now, 10%, just for simplicity reasons, for my comparison. And I go back at the results tab, and I hit show results. So the tool uses all my previous values and the new value for demand-side management.
The value that you put there in the DSM is
Yes.
10% of cutting at energy consumption
10%
due
of energy,
to flexibility.
10% of energy consumption that is cut from that period and moved towards the morning period, 8 to 4, when the photovoltaic is active and producing.
The flexibility is related to when do you use the energy.
Yes, when. It's not load shedding, it's load
It's
shifting.
not reducing the energy consumption, it's moving it to a different zone.
You move it towards the photovoltaic zone.
Okay. This is the only option for the DSM this is the only flexibility that appears in DSM usually, or
There are a lot of
it's the main issue, the main properties that is important.
There are several options for demand-side management. We selected for our tool here to have load shifting. So not cutting the load and losing our comfort, let's say, but shifting the load towards a period that we have photovoltaic production.
So just to be clear, because I'm not electrical engineer, so it's not exactly the DSM analysis, it's the DSM results.
Yes.
The results is shifting. The DSM means how do you shift or how much do you shift? Or it's the same thing?
Yes.
You know
how much and how much from each period of the year and for each day. It's a typical, it considers a typical schedule for each season. We kept this simple. We could use demand-side management options for each month of the year, for each for several time zones. But imagine this table would be large, and it will not. It would not be so convenient. So we selected to provide self-sufficiency per season and per time period: morning, night and early morning, and evening and night. Okay. So now that I have activated the demand-side management, the tool gives me a load shifting schedule in my solution. What does it say? You have to move 500 watt hours from this time zone and 380 watt hours from this time zone towards the time zone 8 to 4. And these are for the spring, these are for the summer, and these are the values for the autumn. This is the load shifting proposal, okay, from our tool. Then the user has to have to see what are the loads that may be shifted and what is the consumption of these loads, etc. But this is the target. Okay, this is the proposition of the tool. Then what can we see in comparison with the previous case that we didn't have demand-side management? Because I saw it was also a question. Here I see that the tool provided me the same solution, 3 kilowatt peaks and 1 kilowatt hour in this case. Okay, but now the net present value is higher. The net present value here is higher, of course, because we also actually exploited the produced energy in a greater rate. Okay, not only by the instant consumption, not only by the battery, but also moving loads inside the time period that the photovoltaic produces. How can we see this? From this index, the annual self-sufficiency rate has increased. It was something like 35, now is 41%. Okay, so this gives us more revenues, increased the net present value, increased the IRR, decreased the simple payback period. Okay, and we can see it also here in the monthly self-consumption, the monthly self-sufficiency. Okay, all these values are increased compared to the previous case. Compared to the previous case. This is the demand side management, and this was, I believe, an answer to the question that I saw in the chat. So, I will see this later. There are several cases that I may examine. I have some in mind, or also that I want to show you, but we can also try some scenarios of yours. I want to show you, for example, the zonal charging. Okay, so I hit clear results. Okay, I go to the zonal charges, and now what I see? What do I see? I see that the tool gives me the option to insert the charges of the electricity for 3 different time zones. Okay. For example, in Greece, there is a daylight zone and a night light and a night zone. Okay. It's divided in 2 zones. So I will consider this case and I will enter my data here. So the morning time zone starts at the beginning time, it's at 7 o'clock. The production charges, so it's 1, 2, or 3 zones, okay? You can click or unclick the 3rd zone. The beginning time, it's 7 o'clock, and the production charges are 0.245. Network is the same. Taxes the same. Okay, these are the same. No time zones. The VAT is 6%, and the second time zone starts at 11 o'clock. So at 11 o'clock we have lower charge for the electricity. So I have entered my 2 options, and then I go back to the results and hit show results. The analysis time is almost, it's something more than 1 minute. It's 68 seconds. I have checked several cases. So the new results are here. Go to AC. We have the same inputs for everything. Demand side management, flexibility of 10%. Okay. Well, but what do I see now? I see that the net present value of the investment is 16,700 euros. It has been increased to a large grade. Okay. The system size is 5 kilowatt peak and the battery size is 4 kilowatt hours. And the annual SSR has increased from 41% in the previous case to 56%. Okay, this is due to the larger size of the battery and the photovoltaic that the tool proposes. And of course, the tool proposes this size, and because they give back because the net present value is high, and this happens because the electricity price is high. The electricity price was in the daylight zone. It was higher than the nighttime and higher than the previous case that we have ended. So of course, it is better for us to install a larger photovoltaic size and decrease the energy that we consume from and we purchase from the utility grid. Also, the monthly self-sufficiency has increased and the monthly self-consumption has increased. Okay. This is about the zonal tariff and, of course, how the net present value increases when the electricity price becomes greater. Now we can, I would like to see also the exhaustive case, the exhaustive analysis. So I have to click clear here. I will go and I will use the same charges, but the high ones here, but a flat case, okay, a flat pricing. I will choose a storage system up to 10 kilowatt hours to examine many cases. And I will go to the analysis and choose exhaustive examination. Okay, then I will hit show results. Now I wait to see the results for a lot of different PV sizes and a lot of different battery sizes. What is the net present value and the self-sufficiency for all these combinations? This may not be the most convenient case for a quick analysis and for an analysis that if we want only to examine the case that gives us the net present value, the maximum net present value, we could use the option that we were using in the last 3 examinations. But if we want to see to make, let's say, a more academic review of an investment in this building, we can choose the exhaustive analysis. This will give us back some tables, okay? And of course, all the results, we can download them as and export them as PDF or as an Excel, okay, an Excel file. So PDF, it's just a report for our archive and for comparisons. The Excel is not also a report. It has no graphs and figures, but it has all the values and the numbers that could be modified and used further for other analysis. Okay, so this was the reason that we selected to provide both a PDF and an Excel file. Okay.
Angela,
Yes.
because we are running towards the end of the session, may I suggest that you complete your demonstration and then we can open the floor for more questions, because I think some external stakeholders may want to ask something, so maybe we can give them the opportunity to discuss with you or ask any more for more clarifications.
Okay, I would like to show some more cases and functionalities of the tool, but okay, let's make it more flexible, I believe. If we have some questions, answer, and then if I have more time, I will can show something more. Okay. Here are the results. As expected, I see some tables. Okay, I see that the tool has examined a lot of PV sizes and a lot of battery sizes. Okay, and it gives me the result of self-consumption, for example, for each combination. Okay, for each combination, for 1 kilowatt peak photovoltaic, 2, 3, 4, 5, etc., until 10 kilowatt peaks. Okay, and this is the battery sizes beginning from the 0 size, the case with no battery. What can I see here? I may see that for example, if I choose 1 kilowatt peak photovoltaic, okay, a case that it's not so realistic, but if I choose this, I will have the same self-consumption for every battery I will have. Okay. Of course, because the production will be low enough to take all the generation and consume it locally. What else do I see? The self-sufficiency rate. The self-sufficiency rate increases as the PV and the battery increases. Okay, so for the largest photovoltaic and largest battery, I see that I have the largest self-sufficiency rate. Okay. The case is not the same for the net present value. So the largest value is, for example, for I believe, as I have seen it before, it's this case. So the case of 6 kilowatt peaks of photovoltaic and 10 kilowatt hours of battery. That gives me 19,000 euros of net present value. But however, I can see how the net present value is how it's modified depending on the PV and battery size. And last, we can see the internal rate of return. I have two more analysis to show, but I would agree with Elisa and make and pass to the second part, that may be a discussion. And then if we have some more time, I will give some more examples.
Any questions from the other participants? Or any comments?
I would like to say thank you. I mean, it's very it looks like very efficient tool, and I'm sorry that I'm not electrical engineer, so maybe it's questions that electrical engineer might see it as trivial, but for me it's not so trivial. I want I I I still have some difficulty, which could be trivial, to allocate the DSM capability in these computational tools, integration tools. And what I would like to ask, if the DSM is the system that allocate the energy from one time zone to another time zone. This is called the DSM, or the DSM is the result itself, like you called it here, DSM. You say that, okay, I'm taking 10% and I'm leaving it. That is enough, or you need to say, how do you allocate, or the DSM is how do you allocate it's more about terminology.
Demand side management is an umbrella that may include all several services. I mean, when you demand side management, it's the response of the demand side, meaning the consumers, on some market signals, let's say. Okay, or demand side management can be implemented also locally in my building, because I need to manage my loads in order to reduce my electricity bill. Okay, so load shifting or load shedding and cutting are two services that belong in demand side management umbrella, under this umbrella. Okay, so when I say demand side management in this tool, I consider only the case of load shifting, meaning taking a load, shifting it towards another period of the day. Okay, this is because I want my building to be self-sufficient. I want my building to be grid friendly. So I want the lowest interaction with the utility grid. If I want to achieve a nano-grid, which is the aim of the project, of the Berlin project, okay, and make my building grid friendly, then I have to take my load and ideally cover all my loads from my own consumption, production. Okay.
What it means is also, how do you shift the load? Probably you shift it by battery. I mean, you store the energy in one time zone and you use it in a different time zone.
Okay.
So it's taking into account also the battery, or it doesn't take into account, I mean, in the calculation, in the pricing, in all the analysis, it's all, when you say DSM, it's already taking also the tool that is used to shift the load, or it doesn't say anything about that?
This is a good question, yes, because it could be both of what you say. In this case, in our tool, the demand side management and what we saw as results considers only the load shifting made by the flexibility of the load, not by the battery. The battery is a different case. The flexibility is a different case. Okay, so this is why when I had deactivated the demand side management option, my first table that gives the demand side management schedule was 0. Okay, the battery was used, but all my loads were considered inflexible. Okay, so nothing was moving, nothing was shifting inside the day. We were using the battery. Okay. However, we were using the battery, but nothing was shifted. When I activated the demand side management option, I added the flexibility of the load. I added another service, the load shifting. So the whole flexibility gained by the battery and the gain by my loads increased. Okay, this is what I believe it's an answer to what you asked.
Yeah. I mean,
hope.
Okay, Angela, I think we don't have any more questions from the others, so maybe you can take advantage of the remaining time to show the other examples.
Okay. There is an example, yes, that I want to show you. Let me clear the results. And this is the cost-effective solution. Let's click the results. This is an interesting one Because if I want to maximize my self-sufficiency, usually this will be achieved by the maximum photovoltaic size and the maximum battery size. Maximum, I mean, if I enter some regional values in the PV system parametric analysis here, I mean. Okay, and in the storage system here, the maximum battery size analysis, then if I click the option to calculate the maximum self-sufficiency, most probably I will see that the tool will give me the maximum PV and battery size. Okay, and will say this is the size that you will need to install in order to have the maximum or 100% of self-sufficient building. However, I need cost-effective solutions, a trade-off of the maximum net present value and the maximum self-sufficiency, because if I purchase a large PV and battery, then maybe my investment will be not viable. So what we thought here was to provide the cost-effective solutions, the trade-off. I skip the first tables because are the same results. I believe we got familiar with this. And I go to the last one, which is the cost-effective solutions. What I see here in this figure, this is in the y-axis, the net present value, and on the x-axis, the self-sufficiency rate values. Okay, so I see here some solutions. These are the trade-offs. So what I mean, let's say that I want high self-sufficiency, but also a high net present value. So I say, okay, this is a good solution because it gives me 71% of self-sufficiency and almost 18,500 euros. When I hover this with my mouse, I see that the solution is 7 kilowatt peaks of photovoltaic and 8 kilowatt hours of battery. Okay, I may want, let's say this was the case, the best case, as I see it here, but we can also consider some other cases, okay, that may have a lower investment cost. Okay, this shows us, okay, all the options, the 10 best cost-effective solutions, trade-offs between net present value and self-sufficiency. Okay, so this solution is 7 kilowatt peaks, but a lower battery, 4 kilowatt hours. So I lose some self-sufficiency, I lose some net present value, but maybe the investment cost is lower. Okay, in this case. And of course, I can take an idea from this table and then say, okay, so what I see here, it's that my photovoltaic, it's usually proposed as 7 kilowatt hours, 7 kilowatt peak, sorry. So I may go back, clear my results, and make an analysis for a single PV size of 7 kilowatt peaks. And then, for example, enlarge my range for battery size analysis. Okay, these are options and conclusions that may be taken from my results. I try to give you all the potentials of the whole potential of the tool, of the functionalities of the tool. I may also examine a case from our partners and friends in Cyprus. Here, I may enter now the new values. So the PV system location would be at the facilities of our partners. Okay, so it's, yes, in Cyprus. We would make simple PV size analysis of 40 kilowatt peaks as design, because we know it already, and will give a slope of 28 degrees. Okay, these are the PV system characteristics for the building there. The storage system that we will analyze is up to 50 kilowatt hours. Okay, and then I will consider our consumption of 20,000 kilowatt hours. Cyprus case, demand side management of 10%, let's say, let's keep it the same. The charges would be these or those of Cyprus. And they have some taxes in Cyprus for the ancillary services charge per kilowatt hour and VAT of 19%. I will keep will put a self-consumption policy of 0 point with a compensation of my energy at 8 cents per kilowatt hour. The cost will be the same. And I see here that I have selected a single size analysis for my PV. Okay, only one option is activated, the exhaustive examination. This is because what I need now is to see how my net present value and my self-sufficiency differs when trying different battery sizes, because I know my PV size already. So I will hit show results. And maybe I can compare with a case then that I have no compensation. This is an interesting case. Okay, I see my results for 40 kilowatt peaks size. Okay, what we selected, and for all these options of battery size, I have my self-consumption rate, I have my self-sufficiency rate, and the net present value. What I may see is that the best case in the best case is our battery of a solution with no battery. Okay, this will give me the highest net present value. As I see in this table. Of course, this will give me not the best case in self-sufficiency. Okay, if I want to increase my self-sufficiency, I may, for example, choose 22 kilowatt peaks of battery, but my net present value will be decreased. Okay, let's see now. Of course, this case would be different if the battery cost was lower, because I have selected a realistic, I believe, but at this moment high battery cost. Okay, I have selected like 700 euros per kilowatt hour. If I have an incentive and reduce this a subsidy, for example, and reduce the cost of the investment, then again the results would be different. So the tool has a lot of flexibility for both the financial and the technical parameters that you may enter. So if I select now the pure self-consumption, okay, the pure self-consumption case, and go back, clear my results, and examine again the same scenario. What would I see? Okay. What do I see here? The net present value is always negative. So this shows me that in case there is a in case there is the policy of pure self-consumption, okay, and I do not sell energy to the grid as previously, then the option of 40 kilowatt peaks of photovoltaic system is not viable. Is not my best option. The investment does not return me any profits. So in that case, I may select a parametric size analysis from 1 to 40 and see what is the best case when there is a policy of pure self-consumption. Because 40 kilowatt peaks was a large photovoltaic for this policy. Okay, then I can select the optimal, etc., etc. For example, I can see here the fast solution, the examination of 9. This, I think, it was the only one that I have not demonstrate. Okay. So I have here some results. Okay, there are 3 combinations, 9 combinations, 3 PV sizes, and 3 different battery sizes. So what I see here is quickly see in this range that I have selected, how does net present value, for example, what is the net present value trend? Okay, so I see that I may select a small PV, not 1 kilowatt peak, but smaller than 20, and maybe a 0 battery. So this gives me a picture quickly for my case study. So now that I know that this is 1, and in 20 it's already negative, and it's negative, and the only positive value is at 0, I may change my examination ranges. So I may put this up to 20 and maybe put this up to 10. Okay, and make my analysis more realistic. I believe this is what I would like to show. I would be happy if you had any cases or case studies or ideas you wanted to share with us or to examine here. And of course, I would be happy, and we would be happy as a consortium if you would use this tool and have some questions or propositions that you can send back to us. And of course, we will be in touch for any help you need. There is a contact email in the help manual. But also now that we have also some time left, you can ask whatever you want, and we can discuss about this tool. Yes, please.
Yes, hi.
Hi.
Yeah, I entered the panel. It was a bit late when I entered the panel, so I wanted to ask if the recording would be sent to us so that we can go through the presentation when it is convenient for us as well.
Of course, yes. The reason that it was recorded was to share it with all the participants or some people that may also need to see the tool functionalities and didn't have the chance to enter today. Yes.
Okay. Yes, this is a question. Thank you so much.
Yes, these are the results also. I see that for the pure self-consumption policy and for the Cyprus case study, the optimal PV size is 7 kilowatt peaks and the optimal battery size is 3 kilowatt hours. Okay, this gives me the maximum net present value, for example. See how different it is when the PV excess energy is compensated or not. It's a totally different solution for photovoltaic, and this must concern the policymakers. With this case, I believe I have completed the demonstration, and in case there are no other questions, we may conclude this session. Elisa, is this okay with you?
Sorry, Angela, can you repeat?
Yes, I say I believe that if there are no other questions, we can conclude this session because I have covered all the functionalities I would like to demonstrate from my side, at least.
Okay, and if there are any further questions, the participants can always contact us and send us their question. So thank you very much for this, and we will send the link to the recording as well.
Okay, thank you for the organization and the recording. And I hope I will have the chance to communicate and answer any questions about them.
Thank you. Bye.
Bye-bye.
Thank you very much, Angelos.